The title of my talk is An Aripiprazole Analog with Two Binding Modes at the Dopamine D2 Receptor. A solid understanding of the mechanisms governing ligand binding is crucial for rational design of therapeutics targeting the dopamine D2 receptor. Here, we used G-protein-coupled inward rectifier potassium channel activation in cenobioscytes to measure the kinetics of dopamine D2 receptor antagonism by a series of aripiprazole analogs, as well as the recovery of dopamine responsivity upon washout. The aripiprazole analogs comprise an orthosteric and a secondary pharmacophore and differ by the length of the saturated carbon linker joining these two pharmacophores. Two compounds containing 3 and 5 carbon linkers both allowed for a similar extent of recovery from antagonism, being 25 to 40% of control in the presence of 1 micromolar of dopamine and more than 90% of control in the presence of 100 micromolar of dopamine. However, recovery was less prominent, only about 20% of control, upon washout of the 4-carbon linker compound and experimental PET ligand SV3-130, both with 1 and 100 micromolar dopamine. Prolonging the co-incubation time with SV3-130 further diminished recovery. Curve shift experiments were consistent with competition between SV3-130 and dopamine. Two mutations in the dopamine D2 receptor's secondary binding pocket, V91A and E95A, decreased agonistic potency and increased recovery from SV3-130 antagonism, whereas a third mutation, L94A, only increased recovery without affecting antagonistic potency. Our results suggest that the secondary binding pocket influences recovery from inhibition by the studied aripiprazole analogs. We propose a mechanism supported by in silico modeling whereby SV3-130 initially binds reversibly to the D2 receptor, after which the drug receptor complex undergoes a slow transition to a second ligand-bound state, which is dependent on the secondary ligand binding pocket integrity and irreversible during the time frame of our experiments.